So let's look at the wave equation again, or excuse me, the equation for the wave again. And we're gonna look at velocity, acceleration, what's called the wave equation. And so if I write down my equation for a traveling wave, and it's a sine of kx minus omega t plus phi, or phi naught, either one. Again, k is 2 pi over the wavelength, and omega is 2 pi over the period. Right. And so this is the position at any place along the wave. I can get I can look at the rate of motion vertically of the wave. That's just dy dt. Y is the vertical position. Again, if my wave looks like this, right? This is my x-axis, and this is my y-axis. So dy dt is how fast the wave is oscillating up and down, right? And it turns out we call this a partial derivative. You may not be familiar with those, but just roll with me on this for a minute. And this is where I'm explicitly interested in just the time dependence, not the x dependence, or any x dependence that implicitly varies with time. And so all this means is I'm taking a derivative explicitly with respect to time, and so I can treat the x variable as a constant, just like the phi variable. And so the derivative of sine is cosine, and so this becomes minus omega a cosine of kx minus omega t plus phi naught. Right? It's a cosine because I have to take the derivative of this with respect to time, and so the derivative of sine is a cosine, and then I have to multiply it by the derivative of what's inside. As far as the partial derivative with respect to time is concerned, this is a constant, so that's a 0, and this is a 0, and so I just multiply it by minus omega, which is what I get when I take the partial derivative of minus omega t with respect to t. And so what this says is that this is my velocity in the y direction, right? And so this says Vy max is equal to omega a. The maximum value this quantity can have is just omega times a when the value of cosine, when its magnitude is 1. And so we can say when the value of cosine is minus 1. Anyway, Vy varies between minus omega a and omega a. And so that's the maximum velocity in the y direction. Similarly, I can look at the acceleration in the y direction and say it's just the second derivative of that. And we can all do that ourselves, right? The derivative of cosine is negative the sine, and so I have a negative sign that comes from the cosine, but I'm also going to get a negative sign here, and so this is going to become minus omega squared a sine of kx minus omega t plus phi naught. That's the same maximum acceleration we got from a simple harmonic oscillator. So we can also look at the slope. So to get that, we can say, look, partial y, the derivative with respect to x, the derivative of this with respect to x gives us the slope, and so we're doing the exact same thing. Again, we're neglecting the time dependence of that, and we're just saying, look, the derivative of this with respect to x is, and so I'm just doing the same thing. Derivative of sine is cosine, and this is going to give me a k, and so I get k a cosine of omega t, of kx minus omega t plus phi naught. And similarly, I can take the second derivative. So this is the slope. The second derivative is called the curvature, and that's just the second derivative. The derivative of cosine is negative the sine, so this becomes negative k squared a sine of kx minus omega t plus phi naught. And so if you look at these two guys, right, this is the curvature. If you look at these two guys, then you can see they both have a sine of kx minus omega t plus phi naught, right? There, and so and they each have an a. The only thing that's different is this one's got an omega squared and this one's got an a squared. And so if I just do a little eraser work here, I can say, look, partial if I take the ratio of this one to this one, it's just omega squared over k squared, the ratio of those two. We just said over here, I erased it, we just said this is 2 pi over the period. Omega is 2 pi over the period, k is 2 pi over the wavelength, and so this becomes the wavelength squared over the period squared, which is just equal to the velocity squared. This is a horizontal velocity of the wavelength divided by the period. Right? And so what this equation becomes, if I cross multiply, I get partial squared y of x and t, partial t squared is equal to v squared times partial squared y partial x squared. This is called the linear wave equation, or just the wave equation. This is the thing that has solutions that are a cosine omega t plus v, where k is 2 pi over the wavelength and omega is 2 pi over the period. And so this is that's the linear wave equation. So waves obey this differential equation. So if you have a wave on a string, it turns out that the speed of the wave is equal to the tension divided by the linear mass density. Your book shows it to you, but I'm not going to go into it. You can derive it from the fact that from looking at the tension in the rope along its length and looking at the ratio of that from two different points. But basically, we can see that the tension, the speed is equal to the tension over the linear mass density. T equals tension square root of that, right? And mu equals that's equal to the mass of the rope divided by its length, or the mass per unit length. So a rope might have 10 grams per meter or something like that, depending on what kind of string or rope it is. And so if you know the tension and the linear mass density, you can determine the speed of the rope, the wave on the rope. And notice that you can increase the speed of the wave by increasing the tension. This is what a guitar does, right? If you turn the knobs on a guitar, you can change the speed of the wave. Similarly, if you use a thicker rope, you reduce the speed. And so, for example, where's my slinky? You can kind of think of this as a wave if I do this, you can see the wave traveling back and forth on there, right? And now if I make it much more tense, if I do it like this, so I've increased the tension and reduced the linear mass density. I've made this number bigger and this number smaller, right? And so my V should get bigger, and you can kind of see if maybe you can't even see it all. So you can kind of see that goes faster than, say, this one does, right? You should be able to see that. Okay, it's also true on a rope. I'll do some examples for that, but I just wanted to say one other thing. For waves in a fluid, so that could be air or water or anything like that, the speed is equal to the square root of, so this would be the elastic property over the inertial property. Right, and it's really true for this too. The period is the tension is how hard it's stretched, right? That's the elastic property, and linear mass density is the inertial property. For most fluids, we write it this way: it's equal to B over rho, where B is called the bulk modulus, and rho is called rho is the density. And so let me just erase this up here. I'm going to come back to the rope one. B equals bulk modulus. The bulk modulus is just minus